Hi everyone, and welcome to the first lecture of our online course on deep learning systems, algorithms, and implementation. I'm Zico Coulter. I'm going to be giving this lecture, but I'm teaching this course with my co-instructor, Tianchi Chen, who will be giving some of the later lectures. We're both faculty at Carnegie Mellon University, and we're also offering this course this fall at CMU, but we're making all the material public as part of this online course. This lecture is going to be a basic introduction to the topics of this course, as well as cover some of the logistics of the course. As such, it's going to be a bit different from other lectures where we're actually going to go into detail about the methods, the math, the code, etc. This is really just a lecture with slides in it. But we're going to cover a bit about why this course might be of interest to you, why we think these are important topics to know about, and also cover a bit of background on the logistics and setup of this course. All right, so as I said, this lecture really has two parts. The first part is about why you should study deep learning systems at all, why you might want to take this course. And the second will be more about the course info and logistics. So let's jump right in and get started talking about why you might want to study deep learning systems. Now, the aim of this course is to provide you with an introduction to the functioning of modern deep learning systems. And what that means is you're going to learn about how these things work internally. You're going to learn about methods like automatic differentiation, a number of basic neural network architectures, optimization, as well as methods for efficient operations on systems like GPUs. This is how these modern deep learning systems actually are run efficiently on modern hardware. To solidify your understanding, the main effort that you'll put in throughout this course is that through the homeworks, you will develop the NEEDLE library. NEEDLE stands for the necessary elements of deep learning, and it's a deep learning library loosely similar to PyTorch. You're going to incrementally throughout your assignments implement many common architectures and many of the aspects of this library, really from scratch. So why should you do this? Why might you want to study deep learning? And why might you want to study deep learning systems? Well, to start off with, let's answer the easier question first. Why do you want to study, or why might you want to study deep learning? Now, chances are, if you're taking this course, you probably already like deep learning, or at least know about deep learning, and probably have a pretty good idea about why you might want to study deep learning. But I will give a few quick examples anyway, many of which you've probably already seen, but it wouldn't really be a deep learning course if we didn't start off the first lecture with some cool pictures about the things that deep learning can currently do. So maybe you heard about the famous AlexNet architecture, which was developed in 2012, which performed very, very well on the ImageNet image classification challenge. I need to highlight right off the bat, this is not a history of deep learning, nor is it assigning credit to any sort of first elements first architectures of deep learning. That's an argument I do not want to get into. But this was a very, very famous architecture that really, at least as a field and as a technique in the public view, really did turn a corner on availability and power of deep learning by essentially building an architecture that could classify images into one of 1,000 classes much better than standard computer vision techniques at the time. You probably also heard about the AlphaGo system, which was developed in 2016. And defeated not quite the world champion, I guess, or number one, but a very, very highly ranked, essentially one of the world's best players at the game of Go. Now, the game of Go for a long time was viewed as a grand challenge for computer play of games because the number of possible moves at each location is very, very large, and standard techniques like those used in chess just weren't very applicable here. But using techniques from deep learning, this team at DeepMind was able to build a system that could defeat, essentially at the time, one of the best players in the world, and soon after, all the best human players in the world. Much, much faster than I think anyone in the field really expected it to happen. Maybe you've also heard or seen about images like these. These are images of faces generated by the StyleGAN system. And I know we're all used to seeing these things now. We're actually quite used to seeing faces that are not real. We see them everywhere now. But I remember when this post was first made on Twitter. People were advertising this paper on Twitter. And I thought people were joking. I thought actually this was just a set of pictures from the training set that people were joking about and saying they were generated by the GAN, by the adversarial network. But no, they really were, right? These are actually fake images generated by this network. And I think that we almost take it for granted now just how easy it is to generate pictures of fake people, which was a capability we did not have 4 or 5 years ago. A little bit more recent history now. You've likely heard about the GPT-3 system. This is a system built by OpenAI that can generate text. And the way it generates text is essentially writes text one word or one token at a time. So given all the previous tokens in a sentence, it predicts the next one. And then it appends that to the text and predicts the next one. And from this very simple seeming process, we are nonetheless able to generate amazingly complex and coherent pieces of text just from essentially a deep learning system that's meant to predict really a distribution over next possible tokens in text. And in fact here, hopefully it's legible in the video here, but I actually asked GPT-3 to write a summary of this course, and it spit out a very reasonable summary of a deep learning course. In fact, it's actually a very bad summary of this course because says we're going to talk about the theory and the math, and then we're going to cover unsupervised learning and reinforcement learning. But it would be a very good summary of a kind of generic deep learning course that would be offered, that is offered in fact here, and would be offered at many, many universities. You've also probably seen AlphaFold and the AlphaFold 2 system. This is a system that predicts the 3D structure of proteins from their DNA sequence. This, for a very, very long time, has been a grand challenge in biology, understanding how DNA sequences form the 3D structure of proteins that actually carry out tasks in the body. And for a very, very long time, this is a chart here of the progress and accuracy of these systems over many years at sort of a well-known competition on this task of protein folding prediction. And over the course of 4 years, this system, AlphaFold, built by DeepMind, again was able to really produce a amazing scientific breakthrough in the quality and accuracy of this prediction, to the point where effectively you could argue that at least in some restricted cases, this problem is in fact effectively solved. And finally, it wouldn't be 2022 if I didn't include a picture of an image generated by a deep learning system. This is a picture generated by the Stable Diffusion system, which actually was released like a week and a half ago. In fact, it was released on the same day we also posted the video announcing this public course. So they really stole our thunder here. Of course, this also relates to the work done by the DALL-E 2 system and going back for the DALL-E system and many papers before then. But these systems are amazing in that they can take a text prompt and generate that probably no one has ever really thought of before, and generate a very realistic painting in many cases, or image in many cases, that corresponds to that text. So here I wrote the text prompt of a dog dressed as a university professor, nervously preparing his first lecture of the semester 10 minutes before the start of class. I don't know why I would have thought of that thing. You can imagine it yourself. And it was an oil painting on canvas. And you see what the system generated was, well, it looks like a dog dressed as a university professor preparing a lecture. I guess 10 minutes before class. That part maybe is evident in his expression. And it looks kind of like an oil painting. And this is just so amazing, the capabilities that we have in these systems. Now, one thing you may notice about all these examples I've given, except the very first one, is that they are all done essentially at companies. Not actually the last one. So Stable Diffusion actually is done at a relatively small company, but they still have a fair amount of resources that were behind this effort. And the other point I want to make, though, is in case you're a little bit concerned, saying, oh, all this stuff is just happening at big companies, what can one person or a small group of people really do to influence this? I would first of all point to that first paper and the Stable Diffusion paper actually as bookend examples of what a few people can do with the right methods and the right cleverness. But I want to highlight a few examples, too, of smaller efforts that I think have still been amazingly impressive at shaping the field of deep learning. So the de-oldify work, essentially done by two people, is more or less, or was, I believe still is more or less, a state-of-the-art technique for taking old pictures, old photographs in black and white, and creating color versions of these. Now, image colorization has been researched as a topic for a long time, but this system really is an effort of a few people that ultimately achieves, I think, the visually best version of this sort of task that I have seen from this. Done essentially by two people with very limited resources, at least in the initial versions. If you work in computer vision these days, you've probably heard of the PyTorch image models, or TIM library. This is essentially work by one person that wanted to implement a whole bunch of, with some help now, but at least starting out one person, Ross Whiteman, who wanted to implement a whole lot of deep learning image classification models from many, many papers and test them all out on benchmark data. And in many cases, using pre-trained weights from those papers, or in many cases, training them from scratch. And this started at least as a relatively small effort by one person, and has become really the dominant image classification library that we all use academically when we are building these vision systems. And finally, I won't highlight these other ones actually, because these in fact are community efforts. But there's been many other examples of libraries, systems, big sort of code endeavors that are essentially community driven, and that they are for both libraries and frameworks that have been community driven, that have really driven the field forward. And I'll actually mention some of these again when I introduce briefly my co-teacher in this course, Tianchi. So all of this that I've talked about so far probably is not news to you. If you're watching this, you probably say, yes, I get it. Deep learning is great. That's why I'm taking this course. That's why I'm listening to this video so far, if you haven't skipped forward already. But why should you learn about deep learning systems? Why do you actually want to study deep learning systems? Not just deep learning, but the actual architectures behind that enable these systems. And the way I'm going to motivate this is I'm going to show a chart here of such a Google Trends chart of the interest measured somehow in deep learning, the term deep learning, over the past 15 years or so, 14 years. And I'm going to annotate this chart with a few events of note. So in the late 2000s, this is actually when the field of deep learning, in some sense, took off academically. So I was going to conferences at this time, and I remember at conferences like NeurIPS, this deep learning became a thing, a field where there was lots of papers in it every year in the late 2000s. But still, I mean, maybe this is always how academic work happens. Still, there wasn't much, as measured by Google Trends relative to the current day, there wasn't a whole lot of interest in deep learning. It was just sort of an academic trend like many others that you've probably not heard of because they were 15 years old and no one's using them anymore. Then in 2012, as I mentioned, the AlexNet network was released, which, again, this is not a history of the field of deep learning. And I've, of course, should also mention, I mean, though I should, of course, mention that the actual mathematics of deep learning and neural networks goes back well into the 80s and probably before then to the 70s. This is just a sort of recent history, of course. And again, I'm only annotating a few events, not trying to make claims about who was first to do what, etc. That's a game I don't want to play in. But the AlexNet was a very popular architecture, yet still, and to be a little bit of uptick in interest in deep learning, and but still not too much happened. So state of the art performance on image classification, and still not too much happened. So then what happened? When did this start to really take off? Well, a few other things happened in the later years. So in 2015 and 2016, some libraries like Keras and TensorFlow and PyTorch were released. And if you actually look at the timing of when deep learning became truly popular, it coincides much more with the release of these libraries than the actual sort of what we think of as some of the big notable papers or events in the field. And so I kind of want to make the controversial, but maybe not that controversial claim, that the single largest driver of the widespread adoption of deep learning has been the creation of what essentially amount to easy to use automatic differentiation libraries. That's a little bit too simplified, of course. The actual deep learning systems, which we're going to talk about in this course, involve much more than automatic differentiation. But this core technology, which again goes back to the 70s, not a new technology, but the widespread availability, and there were frameworks before that. So before PyTorch, there was Torch. Just not many people used it because you had to learn a whole new language called Lua to implement your models there. So the availability of Python-based frameworks that let you quickly prototype new architectures, new models, this, I think, was the single biggest driver of the explosion of interest in deep learning. Now, one thing you may also see from this chart is maybe, we're in bad territory recently. Maybe something's happening recently. I don't think it is. I think there's often issues with sort of like the latest data in Google Trends. But more than that, I think probably what's also happening is that a lot of these things are just now falling under the umbrella of AI, which I will try to avoid that term. I'll try to be specific about deep learning as much as possible. But probably a lot of what's happening is people are just using the term AI to talk about a lot of these things and not the term deep learning always. So another way of sort of emphasizing this exact same point, I'm actually going to reference a story from Tianqi's work. And I was quite late to the game when it came to deep learning. Despite being around people that were using it, some of the pioneers in the field, I actually didn't start working in deep learning until about 2015. Maybe not surprisingly, about when I could easily prototype stuff. But Tianqi, he was actually working on deep learning back in the day, back in 2012, when a lot of these architectures were first being developed. And in fact, one of his first projects as a PhD student was to write code for convnets that would accelerate their development on GPUs. This is around the same time that AlexNet and such was being developed, and so he was doing similar things at the time. And the figures he gives is that to implement really a capable convolutional architecture for image classification on a data set like ImageNet at the time, it took him about 44,000 lines of code and about 6 months of coding to do so. And I'll make this point later. But Tianqi's a really good coder, and it still took him this long to write a working deep learning architecture. Contrast that with today. Today, if you want to do the same thing, you would probably have to write about 100 lines of code, and you could probably do it in a few hours. And the reason why is because of deep learning systems like PyTorch, like TensorFlow, and now like JAX. And I think we often don't fully appreciate just how much of an enabling factor it is to be able to iterate this quickly. We think of deep learning models as being slow to train and slow to develop systems, especially large ones. But this is amazingly fast. We have an amazingly fast current iteration time enabled by these deep learning systems. But this still doesn't answer the question that I set out to answer, which is, why should you take this course? So maybe you agree now that deep learning systems are great. Why don't you just use them, right? You can just use, I'm sure you already do, right? You probably use PyTorch and TensorFlow and JAX. Why should you take a course about how these systems actually work? And there, I actually think there are 3 reasons I'm going to give for why this course might be right for you to take if you're interested in deep learning. The first reason, of course, is maybe obviously, if you want to build deep learning systems, you better understand them. So, despite the current state of deep learning libraries, where you may say that, okay, libraries like TensorFlow and PyTorch have kind of won, they're the standards everyone uses, it's actually not really true. I think actually the field of deep learning systems is remarkably fluid, as evidenced by the relatively recent emergence of JAX as a dominant framework for a lot of research in deep learning. It's a relatively new thing. This happened in the last couple of years. But I don't think we're done yet in some way. I think there's actually a lot of work to be done in developing new systems, maybe more specialized systems, maybe systems that specialize in some different area or different paradigm for deep learning. But I don't think we're finished with what the final state of deep learning systems is going to look like. And if you want to develop your own frameworks or build upon existing frameworks, and by the way, all the frameworks out there essentially are open source, so you could definitely just download them, the source currently, and start contributing to it if you understand them. If you want to do all that, then this course and some practice will prepare you to do this. Right? So this is maybe the most obvious reason why you might want to take this course if you want to build and contribute to these libraries as well. But that's not the only reason. And the second reason for taking this course is actually the one that I would emphasize most heavily for practitioners in the field. And that reason is understanding how the internals of deep learning systems work lets you use them more efficiently and more effectively. And I really do mean that, right? So if you want to build the scalable models, efficient models that will execute quickly, or that make full utilization of a GPU, you really do want to understand how these systems are working underneath the hood. What is really being executed? How are they translating your high-level description of a network architecture to something that really executes on hardware and then trains and differentiates that system and adjusts parameters and all that? How does that work? And understanding how that works will actually enable you to write more efficient and more effective code. And this is especially true if you're doing research in deep learning. So especially if you are doing things like developing new kinds of layers, new architectures, new structures in deep learning. This will be vastly improved if you understand the logic and the mechanisms behind these systems. I've always kind of referred to understanding deep learning systems as a kind of superpower that can let you accomplish your research aims even if your research aims are not about system building, can enable you to accomplish them much more efficiently. This is probably the main reason why most of you, I think, can and should take this course. But I would be remiss if I didn't add one more reason to this pile, which is that deep learning systems are really, really cool. And the reason why these systems are so much fun is actually very simple. And that is that despite the seeming complexity of these things, I mean, PyTorch and TensorFlow at this point are millions of lines of code. But despite the seeming complexity of these libraries, the core underlying algorithms behind deep learning systems, behind quite capable deep learning systems, to be honest, are extremely, extremely simple. Really, the core algorithms behind every single deep learning architecture, all those advances in machine learning models that you saw that I put up on those previous screens, at least algorithmically, they're all essentially based upon automatic differentiation and gradient-based optimization, at least from a mathematical standpoint, right? Those are the two or handful of algorithms that actually underlie all of this. And then on the implementation side, essentially they are built upon efficient linear algebra, especially efficient matrix multiplies on GPU systems. Unlike, say, an operating system, where if you want to build an operating system, you really have to build quite a bit of code, right? You have to write a lot of code. And so courses on operating systems that take you through operating systems usually build a very, very basic one. And you have to write, even for that, you have to write a lot of code to do anything at all reasonable. But you actually can write, and you will write, a reasonable deep learning library. If you want to be really compact with your code, you could probably do it in less than 2,000 lines of code. Something that will run on a GPU, that will do automatic differentiation, that will have operations like convolutions and convolutional networks, recurrent networks, transformers, all this kind of thing, right? You can do it in almost no code because the actual ideas underlying these systems are simple. And they're also, and I say this, a little bit tongue-in-cheek, but they're also kind of magical. Before I worked in deep learning, I sort of was brought up in traditional machine learning when we derived all our gradients by hand. And that was the big effort you went through when you derived some new model, is you wrote out a bunch of gradients by hand. I remember the first time I built an automatic differentiation library, and I realized that I could form some complex expression, take its gradient, and then form an even more complex expression of its gradient and differentiate through that thing. And do all that despite the fact that I actually would really struggle to even derive that by hand, right? I mean, I probably could do it, but it would take me quite a while to derive this manually. Yet, I could write some code that did it. This is really, really cool. And it's an experience I think everyone working in deep learning should have. All right, so with all that being said, let me give a little bit more now boring information about this course and the logistics of this course. So first up, to introduce myself and my co-instructor, Tianchi. I am a faculty member at Carnegie Mellon. I've been there since 2012. But in addition to working in industry or at CMU, I've also done a fair amount of work in industry. So I was previously at a company called C3 AI. Now I'm a chief scientist in AI research at Bosch and the Bosch Center for AI. And my research in academics focuses on a lot of techniques for new algorithms and new methods now in deep learning. So I've done a lot of work on adversarial robustness, done a lot of work, especially certified and provable defenses against adversarial attacks. Also done a lot of work in what we call implicit layers. These are layers that instead of just being formed by some sort of stacking of traditional operations, you form them by actually solving a more complex operator like an optimization problem or like a fixed point equation. And you actually differentiate those analytically. In fact, according to the current schedule at least, if there is time, we will have a lecture on implicit layers at the very end of this course, implemented, of course, in our own framework. I was also an early PyTorch adopter, and one of my marks of pride, I'm going to quickly sort of not hold a candle to the systems work Tianqi has done that I'm about to show in a second. But myself and my group, we were early PyTorch adopters. We were actually mentioned as the first group releasing third-party libraries for PyTorch. And one of my claims to fame there is that as part of our efforts to release an optimization layer, so this was a layer, a third-party library that would solve optimization problems as a layer in a deep networks, like quadratic programs, if you know what those are. And to do so, I wrote a CUDA kernel as part of PyTorch that could do batch parallel solving of multiple linear systems as part of as one step of our optimization solver. And the real claim to fame there, of course, is that in doing so, I messed up, or rather, I wouldn't standardize somehow the matrix striding that PyTorch assumes coming out of its CUDA kernels, and I introduced a bug in PyTorch's linear solver that I think persisted for like a year after that. That just everyone was so confused about why this linear solver would just randomly crash at times. So that's my claim to fame, I guess, sadly, about deep learning systems. Now, the other instructor is a bit different. So Tianqi Chen is also a faculty member at CMU, and also in addition to this has a foot in industry. So he was the co-founder of the OctoML company, which is a company that now does a lot of support and development for the TVM library. But the real claim to fame is the following. So I'm giving this lecture so I can suitably embarrass Tianqi a little bit in our introduction here. For a long time, I sort of the standard story I will give about him is that in deep learning systems or machine learning systems as a whole, there really are three big players in this field, right? There is Google, of course, releasing TensorFlow, JAX, and many other libraries. There's Facebook, of course, from PyTorch, but also things like Prophet, it's a time series library. And then there's Tianqi. So Tianqi has been he was the original developer of XGBoost, one of the most frequently used libraries for gradient boosting, and still one of the most widely used libraries for tabular data. He was a lead developer for the MXNet library, which was another deep learning framework like PyTorch and TensorFlow. And then most recently, one of the founding developers and core developers of the Apache TVM library. And so he has done kind of an amazing number of things in machine learning systems as a whole, and actually quite excited to be able to teach this course with him. So before now I jump into the details of this course and these lectures, I wanted to offer a big disclaimer, which I think needs to be said here. And what I'm saying here is that we are offering this course online for the first time. We have not done this before, and a lot of the material, especially the assignments, which is the most complex part of this course, is being revamped from the previous version. It's actually being revamped even for the CMU version, and then that will be, they're kind of beta testing this, and then you'll be given the assignment soon after that. But as par for the course here, there are no pun intended, but as par for the course, there are going to be bugs in the content and the assignments, or just in the logistics of how we run things, right? This is the first time we're offering this as an online course. There are going to be bugs. There are going to be hiccups. Please bear with us. There's a saying that you get what you pay for, right? And this course is free. It's free because we want people to be taking it and we want this material to be out there. But we are doing this ourselves and we are putting it together ourselves, and there will be bugs in it. So we apologize kind of ahead of time for this. Please bear with us. We will do our best to fix these things and extend deadlines as needed to account for these bugs, but they will be there, and we appreciate you. You are all beta testers for this course as we create it. So part of the fun of taking an online course for the first time is that you become a beta tester for the course. All right, now learning objectives. What are you going to learn in this course? I've probably made this clear from past slides, but let me lay it out just in very, hopefully, clear terms here. If you stay through this whole course, do all the assignments and do a final project, then by the end of this course, you will understand the basic functioning of modern deep learning libraries, including concepts like automatic differentiation and grade-based optimization from an algorithmic standpoint. You will be able to implement really from scratch, right? Because we're talking about implementing these, without PyTorch or without TensorFlow behind you, but just from raw Python. You'll be able to implement several standard deep learning architectures, things like MLPs, ConvNets, RNNs, or LSTMs, various kinds of RNNs, and then transformers, and do it truly from scratch. And you will also understand and implement how hardware acceleration works under the hood and be able to develop your own highly efficient code. Now, it's not going to be, I should emphasize, it's not going to be nearly as efficient as libraries like PyTorch or TensorFlow. There's still a big gap between the very best that optimization can do and the code optimization can do, I should emphasize, and what you can do to 2,000 lines of code. No question. So we're not going to break any speed records here, but you will be able to create libraries that work on reasonable medium-sized data like CFAR, right? Reasonably sized networks and architectures. You'll be able to develop them, write medium-sized architectures that actually work for these systems, and do it entirely from scratch on GPU with automatic differentiation, with nice optimizers, all that. Now, the course website, which is dlsyscourse.org, has all this information and will have a listing and also posting of all the lectures for the course. And you can look at the schedule of topics to see what you'll be learning there. Now, one thing to emphasize is that schedule, at least the schedule here that I'm listing, is the schedule for the CMU version, which is about 2 weeks ahead of the online version. But we will also post the dates and the videos for all the online lectures as they become available, and it will follow the same structure as the main CMU course. Actually, only this lecture has slightly different slides because there's different logistics for the online course versus the CMU course. But the rest of the schedule will follow the same schedule between the CMU version of the course and the online course, and the schedule is up on the website. It talks about things like covering an ML refresher and background, automatic differentiation, different types of architectures, etc. Now, one thing you will see is that a lot of the lectures are broken down between algorithm lectures, so lectures covering kind of the methodological algorithms or techniques used to solve some or to accomplish some task in deep learning, and then implementation lectures where we will actually implement some portions of this or walk you through some simple live coding of how these things actually are done in practice. Now, in order to take this course, what should you know ahead of time? And to be honest about this, there is some reasonable prerequisites you should have here in order to get the most out of this course. That's not to say that if you don't have all these things, the course is impossible. If you're really excited about it and want to learn some of these things concurrently as you go through the course, you're welcome to. Just know that it will be more effort to do so. But to take this course, you should have some background in systems programming. That means basically, C++ coding, how to compile things, like not just run Python scripts, but actually compile executable code that sort of runs on, runs natively on hardware. Linear algebra. So you should be familiar with vector and matrix notation. So there's no math I mentioned in this lecture, but later lectures will actually require, I will write things like a bunch of matrices and vectors multiplied against each other. I will do things like take gradients or derivatives of these things. And you should know what that means. That means also, and the probably the biggest requirement really is linear algebra. But there's other things too, like calculus. Really, to be clear, just taking derivatives. We don't really do any integrals. There's some integrals in probability, I guess, but we don't do many integrals in deep learning. But you should know when I write things like gradient symbols and stuff like that, you should know what these things mean or have some understanding of it. We can provide some links to refreshers or background material on this, but if this is really brand new to you, this could be somewhat challenging to become familiar with. As well as sort of basic proofs. Now, we're not going to do many proofs in this course, to be very clear. This is really a systems course, but you should be familiar with sort of the basic constructs of how you go about deriving things mathematically. Like, how do you derive a gradient, stuff like this. You need some Python and C++ development background. And a common question that's asked is, how much C++ background do you need? The answer is, I don't think that much. We're not using any advanced features of C++ or anything. We're not even using C++, certainly not C++ 20 and not even C++ 11 or anything like that. I don't even know if that's the right year to be to be honest. I don't know those things very well. We're not using any like unique pointers or anything like that. It's really just C with a few classes in addition. So I see this as actually very minimal C or C++ experience, but what you should know how to do is if we give you a template for writing a matrix multiplication call in C++, so that's, this template would take in a bunch of float pointers and const float pointers and stuff like that, the sizes of these matrices, things like this, where those pointers point to the raw underlying data in the matrix, in the matrices. You should know how to write quickly, a matrix multiplication routine that would multiply these two matrices together. And then most importantly, because this will happen, when you mess up your indexing in C++, because there's no safe indexing there and you have a seg fault of your program, you should know how to debug it. Either through a debugger, or if you're like me, then through at the very least through printf statements that, this is how I debug, honestly, C++ code. But you should know how to fix things when your code seg faults. Right, so that's kind of the level of C++ background you need. Python, you should probably be familiar with classes and such in Python too, because you will be implementing most of the structure of this library in Python, and that you have to be familiar with. But C++ is really sort of for the low level background. You don't need to know CUDA programming ahead of time. We will cover what you need to know for the course, but you need to understand basic C++ programming. And then finally, you do need to have prior experience with machine learning. If machine learning is really new to you, you're much better off taking a machine learning course first and then taking this course afterwards. You will get much more out of this if you're already familiar with machine learning and probably already familiar with deep learning to a large degree, and then take this course to understand more how these things actually work. So if you are unsure about your background, then what I would say is take a look at the first 3 lectures. I guess not including this one, the next 3. And look at Homework 0, which is going to be released 2 days after we officially start the class. This Homework 0 is essentially meant to be a refresher on some basic ideas of sort of traditional ways of writing things. You will implement softmax regression and a simple 2-layer neural network. And you should be familiar with how a 2-layer neural network in using kind of manual backprop. And you should be familiar with that. You should have seen this before. And maybe with a bit of refresher, be able to do that relatively quickly to know this course is right for you. So if this thing, and one of these you actually will also write in C with the C++ backend. But if that is very challenging for you, then probably you should take some other material before you take this course. But if all those things are pretty straightforward, or really can be made more straightforward again if you brush up a little bit, then this course is likely the right level for you. Now, there are 4 main elements to this course: the video lectures, of which you are watching the first one, programming-based homeworks, a final project done in groups, and interaction in the course forum. And it's important to take part in all of these in order to get the full value of the course. I really think that each of these components plays a crucial role in really understanding the material. Even if, for example, lectures are not directly used in the homework, they're still very important to know. And even if the forum is, in some sense optional, it's very valuable to sort of get interaction with other students taking the course in order to get the most out of it possible. I do want to emphasize that this online public course is offered really independently of the CMU version. So we can't offer CMU credit or things like this for taking this course, even if you pass and do well in the course. But what we will do is, for everyone in the course who completes the assignments, gets an average of 80% or higher, and submits a final project, you'll receive a certificate of completion for the course to sort of indicate you've completed it. We'll somehow make it official, probably post it on the website or something so you can have an official link to it and things like that. But you will receive a certificate of completion for personalized to you that in some sense certifies you've taken and completed this course, even in an online, even just in some sense, in the online public version. Because it is a lot of effort, and we do want to ensure that you have something to show and some sort of record that you've completed this and done it successfully. Now, I'll end by just describing each of these a little bit in each of these 4 elements in a bit more detail here. So the video lectures themselves are going to be essentially in the format you're watching right now. So they will be live recordings of the lecture. They will consist of slide presentations like this one, but most won't just be this. I think this is the only lecture that is just nothing but slides. The rest will all also have things like mathematical notes to them, derivations, and in many cases live coding to illustrate some ideas. Videos for all the lectures will be posted to YouTube or other video sites. We're going to try to make them available on a few different video sites so that they can be accessed globally according to the course schedule. And videos will be available to everyone. So because they're on YouTube, anyone can watch them. So you can actually watch without officially enrolling in the course. Many of you probably are watching without officially enrolling in the course. They don't require registering for the course. One thing I will mention, which you can probably tell from this if you've made it this far through the lecture so far, is that these lectures are taken in one take. We're not doing a lot of editing here. Essentially, we are recording these live, and we will, with minimal, be cutting at the beginning, at the end, or if something really goes bad, cropping in the middle. We're mostly going to do these in one take, and with all the hiccups and such that happen in a real lecture. So this is sort of a online version, but still kind of live stream. Think of them as live streams of lectures. The second component that I mentioned was programming assignments. And this is actually, if I would to say, this is probably the most important component of the class. So in addition to homework 0, which is kind of a separate thing in and of itself, there are 4 homeworks 1 through 4. And these 4 homeworks take you through the process of building different aspects of this Needle library, this minimal Python deep learning framework. Okay? And in particular, you're going to first develop an automatic differentiation framework for Needle. Then you will use this to build a simple neural network library with things like modules for the neural networks, optimization techniques, data loading, that kind of stuff. You will then implement linear algebra backends on both CPUs and GPU systems. And finally, you'll use these things to implement a number of, in the 4th assignment, a number of common architectures like convolutional networks, recurrent networks, and possibly transformers. Each of these assignments builds on previous ones, and you actually have to complete them in order. You have to complete the first assignment before you can do later ones because they build on each other. And this process of building this library really is the key component of the course, and it is how you will learn the most through it. So anyone can watch the lecture videos, but in order to submit the assignments, you do need to officially sign up for the course, right? So you have to actually register for the course. So if you're watching this video just on YouTube and have not signed up for the course yet, if you want to submit the assignments, which is really the way you learn this material, then you sign up for the course and you will get an account to submit assignments to our auto grading setup. Now, one thing I want to mention is that the homeworks are entirely coding based. There's no derivations, nothing like this in the homeworks, or whatever derivation we have, it's sort of implicit because then you have to code it up afterwards to know if it actually works or not. The homeworks are entirely coding based, and they're all auto-graded. This is actually true for the CMU version too. This is the exact same in the CMU version of the course. Everything, there's no theory questions on the homework. It is just program assignments, all code-based. And it's graded through our own auto-grading system that I've actually been developing for a few years. And this auto-grading system works a bit differently from others you might have seen. I'll document this a lot in a future lecture, actually a separate video about the auto-grading system I'll post soon after this one. I'll run through the process of submitting code to this auto-grader. But the big difference that I'll just highlight right now is that in this auto-grader, you actually run all your code locally, rather than submitting like your code and having it run on the auto-grader, which causes all sorts of problems because the environment in the auto-grader is never the same as the one you've coded on locally. So you actually do all your execution locally, and you only submit answers. So the answers and check against reference solutions in the auto-grading system, which makes it much more efficient, much faster to run, as well as sort of makes it a little bit less painful in terms of debugging like environment setups. So I'll go through all of that in a second in a later lecture. It also means that essentially running in CodeLab environments, at least currently, I know CodeLab's changing monthly, so we may run into some hiccups with CodeLab, but at least currently you can do all the assignments in CodeLab and submit them, execute them all in CodeLab, and do all the auto grading and use that. And as I said, I will go through that, the setup and at least the desired workflow for how you should do assignments. I'll go through that in a separate video in a few. Probably posted actually concurrently with this one, but in a few more in a few days. All right, the second to last component is the final project. So in addition to homeworks, there will be a final project, and unlike the homeworks, which are to be done individually, the final project should be done in groups. So you will form groups. There will be posting on the forums to form groups as the time comes, done in groups of 3, especially for the online course. If you want to find a group of 1, or if you find bigger groups, it's certainly fine. The point is to form a group and do a final project. And the idea here is the final project involves developing some new piece of functionality for Needle. So it's like kind of homework 5, designing homework 5, right? Well, to be clear, it's homework 0 and homework 4 are the homeworks, so your final project is like homework 5. You develop some new functionality, capability to the Needle framework. It's really important, though, that this final project involves some kind of extension to Needle, not just implementing some architecture, and certainly not just implementing an architecture in PyTorch TensorFlow. You can't just do that as a final project. It really has to be an extension of the Needle library. Add a different kind of hardware acceleration to the back end. Our GPU work is going to work on CUDA, using CUDA libraries. So you could do one that uses OpenCL or maybe optimizes for the M1 Apple chip, stuff like this, right? All these things are possible, or maybe you do sort of hardware fused optimization for fused operators and things like this. These are all potential projects. We'll also post a few more possibilities, but the idea is that you want to do some extension of Needle as your final project. And finally, the last thing is the course forum. So for those that sign up for the course, and actually, again, this part requires you to actually enroll in the course. When you enroll in the course, you will soon thereafter get an invitation to join the class forum, where you can log in after this class, watching this lecture, if you haven't done so yet. And you should use this course forum essentially as a resource to discuss and talk about the aspects of the course. You can and should ask for help, for example, with assignments in the forum. We won't be able to answer all questions. We, the instructors and the TAs, won't be able to answer all of them, just due to sort of availability. But please do upvote questions that you find important and relevant that you are struggling with maybe, and we will try to answer the most upvoted or the most liked questions to be sure that they're not sort of widespread issues that everyone's encountering. But then also please do help by answering questions from other students, right? We want to form somewhat of community around this course here. So please do not just post questions, but also see if you can answer questions from other students. The more you're able to do that, the more everyone kind of benefits. You can ask for help, and that does include, in some cases, posting code. But please, we have further instructions are posted in the main welcome message in the forum. But we do have some sort of formal rules. But the reality is you can do things like post code and stuff, and you can even share small amounts of code. But please be reasonable. Don't just verbatim share entire solutions on the course forum. You get the most out of this course by implementing the assignments yourselves. And if you post your code, then that makes other people not able to have that experience, or they just then end up copying the code and not writing it themselves. And so be reasonable when it comes to what you post in the forums. You can absolutely share code and share at least snippets of code and things like this. Again, it's an online course, so you could in some sense do whatever you want, but at least in the public forum, please do be sort of reasonable in terms of not trying to give away content for people that would rather not sort of see full solutions posted for the assignments. All right, with that, I'm ending the first lecture here with just a few parting words. So we're really excited to be able to offer this course publicly, and we really look forward to having you in the course. And if you do have feedback or comments for us, please let us know. Now, it may not be possible to make changes during this offering, but we're making this course public because we want it to be a resource for those that are interested in deep learning systems or just interested in deep learning as a whole. And if you can give us feedback that can help us improve at that mission, we appreciate it. So we look forward to having you in the course. As I said, I promise the next lecture is much more contentful. So if you got through this and said, hey, I haven't learned anything yet, where's all the content? Look at the next lecture next. It will cover some of the basics of machine learning. And then soon we'll get into automatic differentiation after that. But we really look forward to having you, and we hope you enjoy this course as much as we're enjoying putting it together.